Okay, so now we start the last chapter for this course, lithography using self-assembly. So we will talk about three self-assembly methods. That is block copolymer self-assembly, anodized aluminum, and nanosevere lithography. So they are the most popular self-assembly methods. The main advantage for the self-assembly is that they are low cost. They are low cost. You do not need any lithography clean room equipment. You do some chemical process, so you get the pattern. But the limit is normally you can only get periodic patterns and usually without long-range ordering. So now we will look at the first one, die-block copolymer self-assembly first. So why we need block copolymer? So in this case, we have two polymers. Here we have PMA and polystyrene. So we dissolve PMA and polystyrene in this tetrahydrofuran solvent. We dissolve it, then we do the spin cut to form the film. Afterwards, we remove one of the block. In this case, so we use the cyclohexene at 70 degrees to dissolve the polystyrene. So what you see here, this is the PMA. You can see there is the phase separation, so you have the phase separation, but you get random pattern, and also the feature size is much bigger than 1 micrometer. So this is not useful. So you also have the nanostructures with some periodic nanostructures. So we have to use a block copolymer. So in this case, you can see we have block A and block B. So this one can be PMA, and this block can be polystyrene. So the difference is that so when we have the block copolymer, they are connected. So this chain here and this chain here, they're connected. But when they're connected, they cannot be well separated. As a result, they will form the nanostructure periodic patterns, something like this. So what pattern will be formed depends on the relative volume of the two blocks. For example, here we have block A and block B. If the block A volume is very small, so you form the block A will form spheres embedded in block B. Then more block A will form the cylinders. When we have the even more, we form this double diamond. So when the volume of block A and the volume of block B is the same, so we form the laminae. So this is the block copolymer self-assembly. So this will give you some numbers. For example, from 0 to 21%, you form the sphere. 21 to 33%, you form the cylinders. 33 to 37%, you form this double diamond structure. So we have the close to 50% equal volume of A and B. You form this laminae structures. So this will work both in the liquid and also at the film format. But when the cell assembly occur in the liquid, what you get is called you get this micelles. So micelles. Because this is the micelle. Because this is the block A and this block B. This is what happened in the liquid. But for the lithography, we do not want this liquid. So we need a thin film. So we need a thin film for the lithography purpose. Then when we have the thin film, we can do the pattern transfer to the sublayers. So from here we can see that we can form, for example, we form if we want the line array. This is the line array pattern. So which one will give you the line array pattern? So obviously this one can give you the line array pattern. This one can also give you the line array pattern if the cylinders they're horizontal. So if the cylinders they're horizontal lie on the surface rather than perpendicular, you can also get the line array. Another pattern is the dot array. We got something like this. So one periodic dot array, hexagonal. So which one can give you dot array patterns? You can see here, this one can give you this is not hexagonal, this one is like a face-centered cubic. This one can give you the pillar array or dot array pattern. This one can also give you the dot array or pillar array pattern. But here, the pillar is perpendicular to the wafer surface. Now here one example of the block copolymer self-assembly. This is the dot array, this line array. So here this is the dot array and this is the line array. So this is after self-assembly, after removing one block. This one, B and D, is after etching into the silicon nitride. So here is the silicon nitride pattern. So here in this case, so we have the polystyrene block polybutadiene. So the other block is this one, polybutadiene. This one gives you a very high resolution. So the most attractive feature of the block copolymer self-assembly is very high resolution. You can easily get feature sets down to 10 nanometer. So how to do the experiment? First, we need the film. So the film can be formed by the drop casting, dip casting, or spin coating. We form the film. So after we form the film, we need to treat the film to increase the degree of the ordering. This can be done by annealing above the disorder transition temperature for several days. But this time, you see, it takes very, very long time. When you do the very gentle for a very long time, you got more ordered, more periodic patterns. But this is too long time for the production. To reduce the time, what we can do, one thing you can do is to get some solvent vapor. For example, you can put some toluene solvent vapor. So we have the solvent. So this solvent will swell the film and make the polymer more mobile, make the polymer chain more mobile. Then it will speed up the self-assembly process. But there is a Canadian professor who used the microwave oven. She used the microwave oven self-assembly. So this is the microwave oven, for the kitchen, normal microwave oven. So what she did, so you have this microwave oven, and you put the beaker, you put some solvent here. This can be, for example, this can be a toluene. Then you put your wafer here. So we have the microwave, but the solvent will heat up. Then it will be vaporized. So the vapor will come to the wafer surface. So the vapor of the solvent will come to the wafer surface. On the other hand, the wafer itself can also be heated up. So the microwave can also heat up the wafer. This way, you get very fast the self-assembly, take just a few minutes. So you can do the self-assembly within just a few minutes using this microwave oven. But what you get here is not, you have a periodic, but this is no long-range ordering, short-range ordering, not long-range ordering. So to have this long-range ordering, we need to do some alignment. We need to do some alignment. So how to align the self-assembly process? So one way to do this is to use the temperature gradient. For example, you can make this. First, you do the annealing process. You heat up. Then this one, you keep this one hot, higher temperature. This one cold. So you have this temperature gradient, so hot, cold temperature gradient. So the cold part will nuclear first. Then it will propagate. From here, from the left to the right. Then this way it got aligned. So here the cold end serve as the template that orient the rest of the film and then propagate to the right side. Another way to do this is to do in the presence of the gradient in solvent vapor gradient. So more solvent vapor here, less solvent vapor, more solvent vapor on this side, less solvent vapor on the other side, or maybe the opposite. Then you can also get the self-assembled long-range ordering. So one important factor for the self-assembly is the substrate property. In this example, we have block A is shorter than block B. So then the block A will form a cylinder in block B. Now, how will the cylinder be lying perpendicular to the wafer surface or along the wafer surface or perpendicular to the wafer surface depend on the substrate weighting property. For example, in this example here, the substrate white for B. Then you form this, BAB. This cylinder is lying perpendicular along the wafer surface. If the substrate white A, the cylinder will be perpendicular. But this is the case for the cylinder embedded in B. So how about this example here? For the example here, we have something similar. So if the substrate if this substrate, if the substrate white A, then it will form, you first get layer A, then you get layer B, and then you get layer A again. Then you get layer B. Something like this. So when the substrate white A, you get A, B, you get something like this. So if the substrate white B, then you get B, A, you get something like this. B, A, you get something like this. But how to get this perpendicular layout? But then we need the substrate to white A and B equally. If the substrate white A and B equally, we can get this perpendicular orientation. So how to make the substrate white block A and B equally? So what you can do? So here we have like for example, we have this one, PMMA block polystyrene. So what surface we have same surface energy to PMMA and also to polystyrene. So this way we have neutral surface. Now this one can be utilized by PMMA R polystyrene. So here is B, a block polymer. So what is R? R here means a random. For example, you have this PMMA polystyrene, PMMA, polystyrene. You have this random. This is the random. For the block, it is like a M. Then you have this S polystyrene. This is the block. So this random copolymer, when they have a similar volume, if this one 50% volume, this one 50% volume, here also 50%, then this random polymer will have the same surface energy to white A PMMA or to white polystyrene. So this is neutral. It's white PMMA and polystyrene equally. But how to make this random copolymer on the surface? This can be done by using the brush. You form the brush. So this brush is the PMMA polystyrene brush. We have this brush, and you will wet the copolymer evenly. Then you form this, perpendicular arrangement. So you form this perpendicular arrangement. This is very important. This way you get the line array. You get a line array pattern. We will come back to talk about this brush later on. So when we do the lithography, we want the pattern to be directed or guided. We don't want, this one is random pattern, but we want it to be guided. How to get the pattern? There are many ways. One is that we can use electrical field, shearing force, surface control of the wettability, chemical pattern, nanostructure surface. So we will look at the nanostructure surface first. So the idea is very simple. So you pattern the substrate with some nanostructures. Then in this example here, you have this PFS. This is the polystyrene. This PFS is polyferrocyanide dimethylsilane. So then you do the self-assembly, insert the trenches. You can see they are well aligned. They are aligned along the structures already patterned on the substrate. This way we get this guided aligned self-assembly. But here you have this only one block show up. How about the other block? So how to remove one block and leave behind the other block? So here you have, for example, after self-assembly, you get something like this. This is the PFS. This is the so here this is the this is the PFS. This one is polystyrene, PFS polystyrene. So how to remove? So how to remove polystyrene? So you leave behind a PFS pillars. This can be done by oxygen RE process, oxygen plasma action. So oxygen plasma action can remove polystyrene easily, right? But this one, poly PFS, this one here, polyferrocene dimethylsilane. So this one has the ferrocene, that is it contains iron. And it also silane, so it also contains silicon. So when the block contains iron and silicon, the oxygen plasma will not etch it away. So you leave behind, it will be left behind. This is the pre-patterned substrate. So we can also work with the shear force. We use the shear force. So when we have the shear force, how to apply the shear force? So you press the copolymer film on the substrate between two plates, then you pull it. So we pull it, it forms the shear force. In this example here, the A forms the cylinder in B. A forms the cylinder in B. If we pull it, you can see they are well aligned. They are well aligned along the same structure. But again, we need a pattern transfer, so we need to remove one block. This is done by using this RuO4 staining. So how does this work? This one is the vapor. So you have this vapor of this RuO4. This one will react with the polystyrene block. As a result, the polystyrene block here will have this ruthenium metal inside. So when this polystyrene has the ruthenium metal inside, it will be resistant to the action. The oxygen polymer will remove the matrix, but the cylinder will be left behind because it contains this ruthenium metal. Then you can do the pattern transfer into the substrate. For this example, it is the polystyrene block. I believe the other one is the PO. This is the polyethylene oxide. The polyethylene oxide. So this one can be removed by the oxygen polymer, by CF4 polymer. But this one, polystyrene cannot be removed. Because it contains a ruthenium, Ru. The third example is the chemical pattern. This is the chemical pattern. So here you can see here. So we have this one is the chemical pattern on the surface. So how to pattern the surface with different energy? In this case, we use the EUV-IR. This is the extreme UV interference lithography. So first we have the we have this brush. This is the polystyrene brush. Then you do the interference lithography using the photoresist. Then you use photoresist as the mask. Using the photoresist as the mask, you can etch away one block. You can etch away the brush. But this area here has no brush. This area here is the brush, is polystyrene brush. This is the PS brush, polystyrene brush. So this part, oxygen polymer will make it hydrophilic. This part is polystyrene brush. It is hydrophobic. Then you apply this block copolymer, you do the annealing process, you get this self-assembly. So here, this one is the polystyrene block. This one is the PMA block. That will get closer to this hydrophilic part. So how to make the polystyrene brush? This can be done by using the polystyrene with one end terminated by hydroxy group. So on the surface, it's also terminated by hydroxy group. So this is easy to do. Then you do the high temperature annealing process, 160 degrees, for example, 160 degrees for maybe 2 hours. So this will work. 160 degrees for 2 hours. Then this will become water. So this way you have this polystyrene oxygen. So the oxygen will be bonded to the substrate. This way you form this monolayer. You form this monolayer with a brush. Now this brush, this is called a graft tool. So you graft the polymer film. You graft the polymer from the film onto the substrate. Then you can remove the bulk of the film. You leave behind monolayer with the brush. Another one is called the graft from. This graft tool. This graft from. In this case, you have the substrate. So you do the polymerization along the substrate. You grow the polymer. You do the polymerization starting from the substrate. You grow the brush from the bottom up. This is called a graft from. Either way, you can form this polymer graft. But in this case, you have this OH group. It can also be like. But this one will also work because here you also have this hydroxy group. Here's the example of this process. In this case, this area has no pattern, so we have this random fingerprint pattern. You can see the distance, the pitch here is 48 nanometer. 48 nanometer. This is the natural pitch. So the lower part we have this grating pattern. So this grating pattern is pattern. We have this pattern here. So the pitch here is also close to the 48 nanometer. So you form the very nice periodic patterns. So here you can see this one this S means a substrate. So the substrate, the pattern here has period is 47.5 nanometer, which is close to this 48 nanometer natural period. You see, very nice self-assembly. But this one, 52.5 nanometer, does not match 48. You get lots of defect. The same thing here, 45 nanometer, you also got lots of defect. Now we want to talk about block copolymer lithography. So when we talk about lithography, that means a pattern transfer. So when we have this block copolymer, we have this block copolymer, one block, another block, one block, another block. There are no pattern, so the surface is still flat. You get flat surface. In order to do the lithography, we need to selectively remove one block and we leave behind the other block. So how to do this? This is the block copolymer lithography. The first example is for the polystyrene and polybutadiene, polystyrene block polybutadiene. In this case, there are two ways for the pattern transfer. We can use ozone. So this is ozone. So the ozone will break down the polybutadiene's carbon-carbon double bond. So you can see here. This is the copolymer here. This is polybutadiene. This double bond is used to form the backbone polymerization. They have this double bond on the side chain. And this double bond will be broken by the ozone. Then it will be vaporize. You form this void. Then you do the pattern transfer. You get the whole pattern. Another way is use this OSO4. This one can sustain this polybutadiene double bond. It will go to sustain the double bond. So the metal here, the OS is also a metal. So this metal here will come to this sphere place, go to this polybutadiene place. Then you do the pattern transfer, you etch away. This one has the metal here, it cannot be etched away. So in the end, you get the dot pattern. Now here, this OSO4 has the similar role to this one, to this RuO4. So they play the same role. So then you get the pattern here. So how to get higher resolution? So how to increase the resolution? How to get a very, very high resolution? So we come back to this slide again. How to get? So here we have the pattern here, 10 nanometer. How to get even smaller feature size? Get smaller feature size, higher resolution. So obviously, the resolution depends on the n. N is equal to NA. So n is the total number of the repeating unit. Total number of the repeating unit of the block copolymer, which is the sum of the repeating unit in A block plus the repeating unit in the B block. Now when the n is very, very small, we have the shorter. When the n is small, we have this shorter chain, right? So when we have shorter chain for smaller n, we get higher resolution. But how short this n can be? This n cannot be too small. For example, if you have this one, so only 3 monomers A block, 3 monomers B block. Obviously, this will not form phase separation. On the contrary, you will form the homogeneous. When it's very small, it will form homogeneous material rather than phase separation. So this will not work. That means n cannot be too small. Otherwise, n cannot be too small. Otherwise, you cannot form the self-assembly. You get homogeneous pattern. So what is the limit of n? How to make the n as small as possible? So this depends on the property of the two polymers. If the two polymers do not like each other, if do not like each other, then they will try to phase separate. So what is the parameter that determines whether the two polymers they like each other or they do not like each other? So that means whether they are very different, whether they are very, very different, or they are not so different. This is the factor called K. Factor is called K. But there are many review papers for the block polymer self-assembly. This is one of them. So you can read those kind of papers. So how different between the two polymers How different? How do they like each other or do not like each other? This is determined by this factor of KAB. This is which is called a Floris-Huygens parameter. Floris-Huygens parameter. So this KAB, this number here, is given by this formula, depending on temperature and also those things. So this is the interaction energy per repeat unit. So the bigger the K, the bigger the interaction energy. That means the more difference, the more contrast between the two blocks. So the bigger the contrast between the two blocks, the bigger the K. Then you can have smaller chain loss. You have smaller chain loss. Then you get higher resolution, smaller feature size. And this is given by this formula here. This is the criteria. Kn needs to be higher than 10 to the 0.5. So that we have very big K. So that when the two blocks, they are very different, very high contrast between the two blocks. N can be small. You still satisfy this criteria. N can be small. So when N is small, you get higher resolution. So this is the one way to do the pattern transfer. Another way to do the pattern transfer, this is another example, is the PMA block polystyrene. So at the moment, this block of polymer is the most popular. So for this block of polymer, the number here, the K, we just for this Floris-Huygens, this number here is not very big. So that means the resolution is not so good. Still, it is good. So this it can give you 18 nanometer pitch. So the smallest the pitch for the PMA and the polystyrene block polymer is the 18 nanometer pitch. So we have about 30 kilogram per mole. PMA block 30 kilogram per mole polystyrene. So this gives you the chain loss. Chain how many PMA, how many polystyrene. You get equal number. The chain loss. You get 18 nanometer pitch. So the K is not very big. But the good thing is that, so when the K is not so good, you can get very good, you get better control over the process. Otherwise, if the K is too big, so the two blocks, if they're too different, then it's very hard to work with the substrate. So very easily you get something like this. You get this parallel configuration rather than this perpendicular configuration. Because they are too different from each other. If the surface may wet A or B. But for this case, they are not so different, so you can have this neutral layer that wet PS and PMA equally. But at the moment, this one is the most promising for the production because this material can be made very, very pure. Very pure means the material is very pure with very PDI is close to 1. This is the polydispersity index. Polydispersity index is very close to 1. And very, very pure. Then you get very little defect. So the industry, they get about a few defect over, 1 centimeter square of the periodic pattern. There is only a few defects. This is close to the production. How to do the pattern transfer here? So we know that a PMA can be dissolved. Can be dissolved in the acetic acid. This one can be soluble in acetic acid, but polystyrene is not soluble in acetic acid. But can we remove PMA without removing polystyrene? This will not work because the polystyrene and the PMA, you have the chemical bond. Between them. You cannot remove one block, leave behind the other block. But what we can do? We can do the deep UV exposure. The deep UV exposure, that means you shine the deep UV light. The PMA is this one is the positive resist. So we have the positive resist. The chain will be cut. So the chain here will be cut. This is the PMA. For the polystyrene, it is the negative resist to deep UV. Negative resist. The chain will be cross-linked. This one will become more stable, cross-linked. As a result, you can remove PMA and you leave behind a polystyrene. This method looks very good, but in reality, this does not work well because of the capillary force. So here you have the liquid. You have this acetic acid. So this one is the liquid. So we have the liquid. You get this capillary force. If the feeder size here is very small, if this one is say 10 nanometer, right? You know, if it is only 10 nanometer, you have this capillary force. So the pattern will collapse. The pattern will fall down, will collapse. This is not good. So as a result, this method is not good for the pattern transfer if the feeder size is only 10 nanometer. But what people do? People do with oxygen RE to do the pattern transfer. So that means this PS and PMA, they are both organic polymer, but they will both be acted by the oxygen plasma. But the action rate of PMA is much higher than the action rate of polystyrene. So actually, this one is 3 times faster action than polystyrene action. So why is it like this? So there are 2 reasons. The first one, this one is a linear polymer, but this one you have this benzene ring. So we have this benzene ring. This is chemically stable structure, so this will be action resistance. Second reason, this one have lots of oxygen. This oxygen will help to burn away the polymer in the plasma action. So as a result, you can act away PMA 3 times faster than polystyrene. Then you can do the pattern transfer by the oxygen RE. But when you do the plasma action, there is no capillary force. Then the pattern will not fall down. So last example is the density multiplication, here by 9 times. So here you can see, so we pattern the post. This post is patterned by electron beam lithography. So in that, the number of the post, including the small post, small pillars, is 9 times more than the number of these big pillars. This is different from here. In the example here, we have this 1 to 1 ratio. You have this 1 to 1 ratio, right? So the number of the lines is the same as the number of the pattern at the end. So we do not increase the pattern density. It's the same pitch. But still, this one is useful because if this part is very rough, this can be very rough. But after this process, transition will be very smooth. You get very smooth lines. So this is 1 to 1 ratio. No higher density. But in this case, we get 9 times higher density of the number of the pillars compared to the pillar you patterned originally. So how to do this? So first, we pattern those big pillars. Those big pillars is this HSQ. But this one is the negative zone electron beam resist. So you can form the pillars by electron beam exposure. Then you do the development. You get this HSQ pillars. So this one is the negative resist. Then you function the surface. with the PDMS brush. This is the brush. Then you self-sample a PS block PDMS, polystyrene block polydimethyl siloxane. Then you form this. You form this self-sampled. Self-sampled pattern. Then you need to form the pillars. We need to add away one block and leave behind another block. So polystyrene and PDMS, so which block is easier to etch? So polystyrene block is easier to etch using the oxygen plasma. The oxygen plasma can etch away polystyrene block easily, but for the PDMS, PDMS contains, this is the siloxane. This one contains a silicon. As a result, so this PDMS will not be etched away by the oxygen, but polystyrene will be etched away by the oxygen plasma. So you get this PDMS pillars together with this HSQ pillars. This way you can have very high density. So this method was considered as the most promising route for the bit pattern recording media. So we have talked about a bit pattern magnetic recording media when we talk about non-impedance lithography at the end of the non-impedance lithography. But we know that about 5 years ago, this bit pattern magnetic recording idea was given up by the industry. But nevertheless, you see, this is very great work. You can have very, very high density. You can get up to 10 terabit per square inch for the pitch of 8 nanometer. Okay, thank you.